Okay, so this is Introduction to Statistical Learning, Chapter 10. We're in the applied questions, question number 7 here. Okay, so we're going to use, as part of the ISLR2 package, I think, the default data set, and we're going to build two relatively simple models here. So one is going to be a neural network with these specifications here. So a single hidden layer with 10 units and dropout regularization. And then we're also going to create a simple little logistic regression and compare the performance in terms of, it doesn't really specify how to compare the performance, but it does refers to labs 10.9.1 and 2 for guidance, and there they are using absolute error. So that's what we'll use. Okay, so here I'm just installing the packages. ISLR2, GLMnet. I don't think you actually need this one. This is for the logistic regression, or you can just use the base functions in R. That's fine. When I was first trying to do this, I couldn't get this thing to work. And so and I finally isolated the problem to there's a different Keras package. And so I believe you need to use Keras 3. At least I needed to use it for working on Colab here. So the TensorFlow here was part of my attempts to get this whole thing running. But I think if you just had Keras 3, you could work it. But I didn't want to delete this because I'm actually not sure what allowed me to get it to work. So I have them all up there. Okay, so first we're going to get the default data set up. So I've called it up here, and I've kind of changed things around a little bit, or I've kind of modified the variables. Let's just look at what default looks like here. Head default. Okay, so this is what default looks like here. So we have whether or not a person defaults, yes or no, as a factor, whether or not they're a student, yes or no, their balance and their income. And in order to make especially the neural network kind of work well, we will often standardize these variables. So balance and income, I use scale, which just makes them standardized normal variables. And then for the factors here, I have turned them into integers of 1 or 0. 1 if there is a yes in that column, and 0 if there's a no. Again, so you can see how I did that there. Okay, so now they're integers instead of factors. Okay. Now at the end of this, we're going to compare the performance of a neural network against the performance of our logistic regression. And even though the question does not specify, I am going to compare them on a test set of data rather than just the whole data set here. So I need to break my data up into training and test data. So that's all I'm doing here. Okay, if you've been watching these videos, that that little phrase, called a phrase or a little stanza of code here, should be somewhat familiar. So we specify how much data we want in the training set, 70%. And so now we convert that to how many actual observations that is. And I randomly sample that number of observations from all observations. And then I call my training set the full data set with just the rows from the training index. And the test set, everything else. Okay. And then I further specified X and Y train and test sets here. What is train? Well, the training data is student balance income. What is Y, the outcome? Y is whether or not they defaulted. Okay, so now we have our neural network up here. And I'm not really sure what to tell you about it, other than, here's what it looks like, or here's one way of it. So remember, we wanted a single layer, so we specify that single layer by saying a layer, and we wanted 10 units. Okay, we give it an activation function, the shape of the data, etc., etc. And we wanted dropout regularization, so we can accomplish that here with this command. And so I'm using 40% because that's what was in labs 10.91 and 10.92. And then we have an output layer. So we have another layer here that's just one unit, 1 or 0. Okay. All right. And then we need to compile everything. So we need to specify a loss function here, what optimizer we're using, so on and so forth. I wish I was a little bit more I'm reasonably familiar with neural networks and this kind of and this model, it kind of comes out of TensorFlow, I think. But I wish I knew a little bit more about it. But nonetheless, what we have here works. Okay. One thing that we can add. So eventually we're going to run this on the data for some number of epochs here, 100. And I think our full data set is like 10,000 data points, and so we have 70% of that, so 7,000 data points. So there's, maybe that's a lot of data. I don't know. But in other words, if we're looking at all of those data points through a neural network 100 times, like maybe that could take a long time, maybe not. But we can tell our neural network to stop running if a certain criteria is met. For instance, if successive iterations, aren't really making the fit any better on test data, or what on, we can specify all sorts of things. I'll show you what I specified here. But maybe we just stop running because now we're just burning time and compute for no additional gain in accuracy. So the way that we did that was with this callback here. And so here's the callback. So after each iteration, it goes back and checks something. And so what is the thing that it's checking? Well, it's checking what we specify here in CB, where we are specifying an early stop command, and roughly what this is telling, telling the computer is if after 5 iterations the loss on the test data does not improve, then stop. Okay, so yeah. So we run it, and we're just calling that history, so we can look at how each iteration is changing in terms of accuracy on this top panel, loss function on this bottom panel for the training and validation sets. Okay. And so you can kind of track what's happening here. Okay. Notice that the loss is getting better, and that the accuracy is getting better. So by the callback function here, I believe it stops after, it doesn't run the full 100 iterations, I believe, but or maybe it does in this case. But anyway, but here's our, this is how the fit is improving over time. So now we need to compare this to logistic regression. So first we need to find, some measure of the error. So here I'm just using the average absolute difference between the actual data and what is predicted from the outcome. Okay, so we get this number here. And then the logistic regression, we can just run in a few lines of code. So logistic regression, oh, you know what? I did not specify that I wanted this to be logistic regression. Let me pause this for a sec. Okay, so anyway, back here, so we tell R that we're using a binomial distribution here. So we run the regression, and then we make the predictions. Here we have to specify what kind of prediction we're making. Response, notice that we don't do that for the neural network. But anyway, we go back and we take the average absolute difference, and we see that they are pretty comparable. So anyway, I think that is it for this one.